I think I said that the final is two pieces. One's in class, one's online. For the online final, you're going to have to select a random sample from a population. I'm going to give you a population of data, and I'm going to say to you, select, I don't know, 10 to 15 observations, and then you'll run through the statistical tests or whatever it is I tell you to do. And this is the method I want you to use, because when it comes to the final online, I want everybody to have the same sample. Because with the same sample, everybody's going to have the same sample statistics. Meaning, if everybody had different samples, that means I'd have to calculate everybody's sample mean. I'd have to calculate everybody's sample standard deviation. I'm not going to do that. So, I'm going to make you choose the sample this way, because this is a way to choose a random sample. And it's one of the ways, I guess, to choose a random sample. And so after you learn it, this is the method I want you to use on that final exam. Okay, everybody clear on that? All right. So it's using the random numbers table to take a sample. You know what I'm going to put it over here. This board in a minute. So using the random numbers table to select the sample. Okay, so how do you use it? Well, the first thing you have to know in order to use this table is the population size. And remember, we designate the population size by n. Okay? The second thing you do is you say how many digits. In n. So let's go back to the example over here. What's the population size? Because we're going to use this data set over here, this population, to take a random sample in a minute. But in regards to New York City commuters, how many? What's the population size? 3 million. Okay, so we got 3 million. How many digits are in that number? 7. The third thing is to group random numbers. Oh, I should tell you what page it's on. By number of digits. In n. And so there is a random numbers table in this book, and this is the one I'm going to have you use on the final. And so if we go to, let's see where it is. It's in appendix, oh here it is, appendix B, page 771, is a table of random numbers. And in this table here, you can start any way you want. You can go down, you can go across, you can go up, you can go down, you can go any way you want on this table. However, the way I want you to go is I want you to start in the upper left and go left to right. Okay, so that's what we're going to do here, and that's what we're going to do on the final exam. All right, you're going to start on this page right here, 771. You're going to go to the top left and read the numbers across. And before we get there, though, it says group the numbers by, and then the fourth thing is to select a sample. Based on the grouped numbers. Okay, so what we're going...
What does number 3 say?
Yeah, I know, my penmanship's pretty bad. Group random numbers by number of digits in n. So that means what we're going to do is we're going to put up the random numbers. Well, I'll just write them small. And so what I'm going to do is I'm going to take starting at the upper left, and I'm just going to go across and put the numbers up on the board, and I'll show you how to group them, etc. So it's what? It says 02711, and then it says 08182, and then it's 75997. Then we have 79866, and we have a 58095, and then we have 83319, 80295, 79741. I'm just going to put one more up here. 74599. Let's see how many observations we can get here from this population. Yeah, I probably should have said 9 million. 9 million would be a lot better because we go through this a little quicker, but we only said 3 million, so you'll see what happens. 599. You have to find observation 1,827,549. Third one. 7798665. You have to go find observation 7,798,665. The only problem is there's no such observation because it only goes up to 3 million. So you pass on that group and you go to the next group. X 8095833. You have to go find observation 8. No, there's no such person as 8 million. Then you go to observation X 1980295. 1,980,295. And so that's how you sample randomly from the random numbers table. And let's say that in this case, the sample size n was equal to 100. Little n is the sample size. Okay, so let's say that whoever was doing the study only had time and money for 100 observations in the sample. So what you do is you go into the 3 million and you pick out 100 random observations. Ask them the question, get the data. And when the data comes back, 100 observations, and you're going to oh, I didn't even ask you the question. Okay, we haven't even asked the question yet. But so before we get there, everybody understand how to use the random numbers table? Okay, now remember, you have to understand it because when it comes to the final, this is what you're going to have to do. And if you're off by 1, if you don't count the observations correctly, you know, you're supposed to go at observation 738, and you bring in 739, that's going to make you wrong. And it's going to be hard for me to find it. Because I'm not going to go through it over here. If a sample is taken from any population, doesn't matter what the shape is of the population, and n is greater than 30, we can rely on the central limit theorem. Because usually when you go and do your study, you don't know anything about the population. You can't assume the population is normal like we've assumed over here. I only assume it over here because it's good for me to explain it when it comes to the next thing that we're going to do over here, which is related to the central limit theorem. But half the time, or 99% of the time, you go out there and they say, listen, I want you to estimate this or that. You don't have any idea. Here are 3 million commuters. Okay? And these commuters have a mean of 72 minutes. This is mu sub x. Because this is the mean of the population. Okay, so it says over here that when you rely on the central limit theorem, it says that the population of sample means is equal to mu. And that's what you're trying to estimate. You're trying to estimate mu. And the central limit theorem says, this is great. The distribution has a mean equal to that. And so what this says over here is if n is equal to 100, let's say you didn't have time and money for 3 million. It says you only have time and money for 100. Well, let's look at the sample means, of which you're going to get one of them when you take your sample, because each sample has a sample mean. When you go out and you select your 100 observations, you're going to get one sample mean. What does the central limit theorem say about the distribution of sample means? It says that it is normal. These are the sample means under this curve. These are sample means. Those are people. These are sample means. And how many sample means are there? You're going to get one of them, no, but what the rule of combinations said last term was that there are n factorial, so it's 3 million factorial. That's how many sample means that are out there. 3 million factorial. You know what 3 million factorial is? It's 3 million times 200 times 2,999,999 times 2,999,998 all the way down to 1. That numerator is like massive. Then it's divided by x factorial, which is 100 factorial, which is 100 times 99 times 98, but it's still dwarfed by the numerator, times 3 million minus 100 factorial. So really there are, and so these all cross out, and then it's 100 times 99 down to 1. So the numerator still far exceeds the denominator. So there are this many sample means under this curve. This, like, I don't even know what that comes out to. Subtillions. I don't even know what the number is. But it's this big, massive number. And you're going to get one of them. Okay? And so what does the central limit say about this distribution of sample means? It says that the mean of these sample means is mu sub x. So what's the mean of these sample means? 72 minutes. This is minutes over here. That's what the central limit theorem says. Now, if I were to go, so it says here that the central limit theorem says mu sub x bar is equal to mu sub x, which is equal to 72 minutes. And what's sigma sub x bar? What's the standard deviation of this distribution? It says sigma sub x bar is equal to sigma sub x divided by the square root of n. So it's equal to sigma sub x divided by the square root of n. And so what is sigma sub x? Well, here's sigma sub x. It's 10 minutes. Divided by the square root of little n. What's little n? 100. So this would be the square root of 100. And so what's 10 divided by 10? 1. So it says here that the standard error, which it's also called, the standard deviation, is equal to 1 minute. So if I were to go 1 minute to the right, what is the value of all these observations? If I go 1 standard deviation to the right, well, what's 1 standard error? It's 1 minute. And so what are the sample means that are 1 standard deviation to the right? 73 minutes. If I go 2 standard deviations to the right, 74. If I go 1 standard deviation to the left, 71. If I go 2 standard deviations to the left, 70. And these, or this, is the distribution of sample means. based on the central limit there. And so, how do you find the area under the curve of a normal distribution? You go from this is the X bar scale. Why is this the X bar scale? Because these are sample means. This was the X scale because these are observations of people. So this is the X bar scale. You have to go to the Z scale so you can use the table. And the way to go from the X bar scale to the Z scale is Z is equal to X bar minus mu divided by sigma divided by the square root of n. That's how you go from the X bar scale to the Z scale. The formula is a little bit different. And so if I were to calculate Z for 72, it would be what? It would be 72 minus mu. What's mu? 72. What's 72 minus 72? 0. Divided by, what's sigma? Sigma divided by square root? Already did it, it was 1. So what's 0 divided by 1? 0. What's 73? 73 minus 72 is 1. What's 1 divided by 1? This is a plus 1. This would be a plus 2. That's a minus 1. That's a minus 2. And so here are the distribution of sample means based on the central limit theorem. And this is what the distribution looks like with the sample size of 100. Okay, so we're looking for the percentage between 70 minutes and 74 minutes. How do you find the area under the curve between 70 minutes and 74 minutes? Well, you already know it's between minus 2 and plus 2 on the Z scale, correct? So all you do is you go look up 2 on the Z scale. And so if you go to the flap in the book, it's 0.4772 because remember the table gives you the shaded area, and the shaded area is between 0 and the Z score. And so the area between 0 and 2 on the Z score or the Z scale is 0.4772. Similarly on this side it would be 0.4772. And so if one were to ask what percentage of between minus 2 and plus 2 on the Z scale, which is the same thing as between 70 and 74, what's the area under the curve? It's 0.9544. I think it's 0.9544. Did anybody get that? This says that if you have given this, if you have a sample of 100, just 100, there's a more than a 95% chance that when you go survey your one sample, just one, you're going to get a sample mean between 70 and 74 minutes. And let's say you get 70 minutes as your sample mean. When you do your X bar, let's say you got 70. How does that relate to the true parameter? What's the parameter? The parameter is mu. That's what you're trying to estimate. You're trying to estimate what percentage of samples are between 70 and 74. We already said it was 0.9544. So if somebody said to you, I want you to estimate that amount of minutes. I want you to estimate for me the average commute of a New York City commuter. And you go out and you survey your 100 of the 3 million. The central limit theorem says there's a 95% chance that when you get your 1X bar, it's somewhere between 70 and 74 minutes. And how does that relate to the true parameter? It's 72 minutes. So even if you get a number of 70, not too bad. You only have to survey 100. You have to survey 3 million. Central limit theorem says you're going to do something pretty good with just 100. Somewhere between 70 and 74, 95%. Now, you might not get that. You might get something that's 80 minutes. Let's drop down, and we'll drop down to 36. Let's see what happens when n is equal to 36. So I can get rid of this, because all we've done here is we've explained these commuters, what the distribution. So if I were to go one standard deviation to the right, this is the X bar scale. If I were to go one standard deviation to the right with this distribution, how many minutes are we talking about? 73.67. If I go two standard deviations to the right, 74.33, 75.33, 75.33, right? Is that right? Yep. Okay. If I go one standard deviation to the left, 72 minus is 71, 70.33. Yep, and if I go two standard deviations to the right, 60, 70, 69, 68, 67, I think. Is that right? 68, 67, yeah, 2, 3, 333, 71, 72. I think that's right. And so on the z-scale, z is equal to x bar minus mu divided by sigma divided by the square root of n. And so if I were just to convert these to the z, those would be the reference points as it relates to z. And so with this distribution, we'll ask the same question. What percentage are between 70 and 74? Percentage between 70 and 74 minutes given a sample size of 36, it's 0.769698.